All right, so how you guys doing today? Okay, perfect. So the spring break is coming, right? All right. So the just one good news here. I'm done with the grading exam one. Like I told you before, over last weekend, it seems really good. I'm not gonna lie. Most of the people did really well. So I didn't do the exact calculation, but I'm pretty sure it's very high 70s. Meaning, you guys attending all the extra credit chance, right? So you can get 2 points every week. So if you attend every extra credit every week, that's 10 points right there on the top of your exam score. So it's pretty much the same as the class average is like a high 80s. You know what I mean, right? It's pretty much so. Seriously, most of you getting at least A and B right now at the moment. I mean, still, once again, if you think about it, if you did really well on the exam one, then you have a stress free on exam two, because you can draw always low one. But if you didn't do well on the exam one, you can still hope for the better luck and study harder for exam two. But anyway, it seems so far so good anyway. Once again, I didn't do actual calculation, but it seems a lot better compared to other previous semesters. At least 10 points higher. That's for sure. I know. If you think about the extra credit that you didn't add to your Canvas yet, I mean, oh, it's already in Canvas, but not on the exam score. It seems very good. Yeah.
So are you gonna add the extra credit to the exam, or are you just gonna
So
keep it in
I
it?
already had a exam score on the Canvas. You guys see that, right? Oh, if you go to that, I put the extra credit score on the Canvas, so you can double check that. So you can consider these extra credit points as a additional point there. So
Okay.
yeah, you can check it on the Canvas. I always put it almost like every end of the week. So it says extra credit 1, 2, 3. Yeah, I'm pretty sure I did. So.
Did you put the exam in Canvas?
Yeah, I'll probably do it today or tomorrow. But once again, the bottom line is, you guys did really well. This is probably the best class I have read for years. This is looks good. Hopefully, all the way through. Okay. So, but yeah, it looks really good. I'll put the exam score today or tomorrow. But I'm done with the grading. It looks really good. Okay. So anyway, and once again, in case if you didn't do well in exam one, you're not missing anything, like I said before, right? But anyway, you guys did well, most of it. All right, so the last time we talked about arcane. So obviously we're talking about some compounds with a double bond between carbon and carbon. Okay. So the first thing we try to do on this chapter, chapter 7, we try to do the nomenclature first. Okay. So first of all, the most important thing was when you have this type of compounds, you always need to find the longest carbon chain that has the double bond in it. Okay. Because as you can see, this alkene compounds, you have E and E as your suffix name. So once again, think about always your suffix name is very important for the name of the compound. So this is the way. In this way, you have a shorter carbon chain than this part here, but still you need to include double bond between these two carbon. So we actually get pentene structures. 1, 2, 3, 4, 5. So the 10. But we have, and then once you're done with it, so this is a quick review, right? So we have a 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. But I'm going to count the carbon from here instead of here, so I can give the lowest possible number for the location of your double bond. So it'll be 1, 2, 3, 4, 5. So 1 and 2. So once again, whenever you have double bond between carbon 1 and 2, always choose the lower one. Okay? So if you have a double bond between carbon 3 and 4, it's 3. 1 and 2, 1, 2 and 3, 2. Okay? So it'll be 1. This is why we call this one pentene. But additionally, you have what? You have some alkyl group over here, because this is your carbon chain, your base, and then you have additional groups attached to it. It's an alkyl group. So we're gonna just put this as like 2. So 2 carbon ethyl, 1 pentene. Okay. Once again, you can do 1 ethyl, 2 ethyl, 1 pentene. You can also say 2 ethyl, pent 1 in. This is okay. Doesn't matter. Okay. So that's the way you put the number for the location of the double bond. But either way is okay. So that was the last time I think we did. So let's do a little bit more complicated case, so we can be fully understand how we name those type of alkene compounds. So, for example, if you have this one, okay, and this one, okay. So obviously, longest carbon chain will be here, right? You guys see this, right? And also include the double bond. That's perfect. So now I'm going to count the numbers of carbon in this carbon chain. So be 1, 2, 3, 4, 5, 6, 7, 8. Okay. So 8 is opt, right? Opt. And then here's the thing. If I count the carbon from here, I can give the lowest number for this double bond location, ENE location. Okay. But you will give a big number for the location of your alkyl group over here. And also, if you count the carbon from here, you can give a relatively speaking lower number for the local number for alkyl group, but very high number for the location of the ENE. So in this case, like I said, the prefix is not less important than the suffix. Because you always think that the suffix name is more important. In that case, we always wanted to give the lowest possible number for this the suffix name first, and then we care about this one later. So in these two scenarios, you count the carbon from here to give the lower number for the location of double bond, which is 1. And then, so in that way, it will be 1, 2, 3, 4, 5, 6. So it will be 6 methyl 1 octane. That's the current name. Okay. Does it make sense, right? Okay. So, so this is the current name. So maybe on your exam, maybe I can say this is a 3 methyl 7 octane, and you can say this is wrong, this is right. Okay. So because of the double bond or the location of your suffix name is much more important, and we always want to give the lowest possible number for the most important groups first. Okay. So that is why we count the carbon from here and here. Okay. So if I give you, okay, what's the name of this one? Can you guys try just 1 minute, real quick? So maybe just this one here. Just 1 minute. This should be quite easy. Okay, 30 seconds. Find the longest carbon chain and decide which carbon you need to count first. And then locate this double bond and the alkyl groups. Okay, what's the answer?
5 methyl
Perfect.
1
I agree. because you actually wanted to count the carbon from here, right? Because your double bond will have a lowest possible number where that is the number 1. Okay, so it will be in 1 and 2 if you count the carbon from here. But it's okay for this method or this one, doesn't matter. This one may have a quite high local number though, that's okay. Because this is more important than this one anyway. Okay. All right, sounds good. So we'll just move on. Oh yeah, so if you have, in case, probably not do this much on organ 1, I'll probably do this a lot more in organ 2, but still it's very important to know. In case you have 2 double bonds over there, okay? So in this case, what you can do is still count the 1, 2, 3, 4, 5, 6, 7, 8, so it'll be oct. Okay? And then you have ENE for sure, but you have 1 and 2 double bonds in this carbon chain. So in this case, we have 2 means di, right? Because remember, mono, di, tri, tetra. So this is di, so we put di en. So this will be octadiene. But obviously, if you pronounce the octadiene, it kind of not very fluently you can pronounce it, right? So what we normally do is put a. So octadiene sounds much fluently, natural, right? So we call this the, so and then you just need to look at this one. It'll be 1, 2, 3, 4, 5, 6, 7, 8. So 1 and 2, 1, 5 and 6, 5. So it'll be 1 and 5 octadiene. Okay. I think it's okay still. You can do octa 1, 5 diene 2. It's okay, but just need to look at these 2 location of the 2 double bonds in the your compounds, and then make sure you put the di, and that makes the octadiene. Okay. I don't think I will do this a lot in organ 1 because we don't normally deal with this the diene or triene and tetraene so much, but probably organ 2. You guys take your organ 2, right? Okay. So I'll just move on, but in case you may see, that's what I mean by diene or triene, tetraene. So, okay. There's a couple of things we may do a lot actually in this semester though, is actually this one. So this is the double bond in the cyclic compounds. We have a ring structure, and we also have a double bond somewhere in 2 carbons. So in this case, you can actually do pretty much the same. This is the 1, 2, 3, 4, 5, 6, right? So it'll be hex for sure. Okay. And then this is a ring structure. We're gonna put cyclo. Okay. Cyclo. Okay. And but we have a double bond somewhere here. So we're gonna have EN. So it'll be cyclohexene. That is what is this one. Okay. So if you have this one, maybe I'll count the carbon from here. So maybe I can say 1 and 2, so it'll be 1 cyclohexene. Okay. What do you guys think? So, do I have to do this or not?
No.
No, perfect. Because oh, you guys are really good. So the thing is, this is in the ring structure. So if you just say cyclohexene, not cyclohexadiene or anything, there's only 1 double bond here, and where there is, it's the same thing, right? Because you don't, it says connected, and there's no end in this ring structure. So only time you might have to do this is whenever you have this one. Okay. So in this case, you just need to locate the number for the methyl group over here. Okay. So this one makes the 1 methyl cyclohexene. Because we always know the first carbon did always start from the double bond. It has to be in that way, because that's the most important thing. So from there. You're not gonna count the carbon from here, right? 1, 2, no. We're gonna count carbon from here. That is the type of something. We may have alkyl groups on your ring base, but other than that, it's quite okay. Well, but here's the one thing I want to tell you. I actually bought this one because it's a very tricky one. So let's do this one. This is quite tricky. So if you try to name this one here, we have 5, and in the ring structure, so the cyclopentene for sure. And then this will be. Here's the thing. So if you count the carbon from here, so be 1, 2, that will give what? 2 and 3 dimethyl groups only, right? If you count the carbon 1, 2, 3, 4, 5, it will give you what? 2 and 3 dimethyl, right? 2 and 3 dimethyl. Okay, cyclohexane over here, right? And then if you do this way, 1, 2, 3, 4, 5 over here, okay, and then it's going to be 1 and 5 dimethyl cyclopentene. In this case, if you think about these two, makes 2 and 3 makes in sum 5. This one makes in sum 6. So it looks like this is better, right? But the correct answer is this one, 1 and 5, because of the 1. The first number you can give on the name of the compound if it's lower than the other one. You can still go with that one, even though their sum in those two local numbers will be higher than the other. So this is a bit tricky, actually. This is why we count the carbon from here, not here. 1, 2, 3, 4, 5, not 1, 2, 3, 4. So this is tricky. I'm probably not gonna put this on the exam anyway. Yeah.
How come you can't count it from the top, like 1, 2?
Mm-hmm. You hear?
Like from the very top.
You
Like
hit
right
1, 2,
there.
3?
Yeah.
Yeah. Well, why can't we do this one?
Yeah, why can't you do that?
Because if you do this one, okay, so that's a very good question. The basic rule here is between your double bond in the ring structure has to be 1 and 2. These two carbons. Other carbon cannot be 1, because this is the one that is the most important part of your compound. So the other one is actually just like an additional group. Okay. So that is why if we do 1, 2, 3, it's okay. But we have only two choices. Will be 1, 2, or 1, 2. That's it. Because this is very important. The reason why the double bond part in your compound is so important is this is actually where we start the organic chemical reaction. So obviously this part is the most important part of the compound. As you know, in chapter 6, we're gonna do a lot more with this one too. The double bond is special because you have the pi bonds on the top of the sigma bond. So the electrons in the p orbital and the pi electrons can be easily used for next step of the chemical reactions. So normally the one with the double bond can be used for many types of the organic reactions. So we care about this one a lot more than the other, which might be not so minor effect on the chemical reactions, but this one is most important. So this is why we always want to give the lowest possible number for these two carbons. That's why we always start with these two in the ring structure. Okay, makes sense, right? It's but once again, I really don't think I put this on the exam for nomenclature-wise. But this is how we do it. I know it's tricky, but just the double bond is very important. Okay. All right, so next one, I promise it's a lot easier, okay? So this one is what we call degree of unsaturation. So we talk about the unsaturation degree because when we talked about the arcane, we know this all carbons in this arcane compound are saturated by maximum possible numbers of hydrogen. Okay? So they're all surrounded by hydrogen at max possible number. So that means they're all single bonded together, and carbons and hydrogen, everything. But when we get to the alkene or alkyne, you have multiple bonds over there that lose the pair of hydrogen at each time. It goes to single bond to the double bond, and double bond to the triple bond. You're going to lose the pair of hydrogen from the higher in the degree of the bond. So that's what we call degree of the unsaturation. If it's the high in the unsaturation degree, means either this compound has a lot of the multiple bonds or also the ring structure. So either they have a ring structure, numbers of the ring structure, or numbers of double bond or triple bond, multiple bonds, and that will give us the number for the degree of the unsaturation. So if you're high in the unsaturation degree, it means it has a lot of numbers of either ring or multiple bonds inside the compounds. Okay? So if that is the case, we have actually a simple rule we can just follow to tell the numbers for the degree of unsaturation by just looking at the chemical formula. So I'll show you why. Okay? Okay, so if you have for example, this is your compound over here. Okay, you have compounds like this. So this is simply coming from here. But if you compare these two, obviously this is fully saturated. These two carbons is fully saturated with the 6 hydrogen. So this is CN H2N plus. So you have 2 carbons there. So maximum hydrogen can fully saturate these 2 carbons will be 6 because the H2 times 2, which is because N is 2, so 2 times 2 plus 2 is 6. Okay? So that's why this is fully saturated in all single bond with the 6 hydrogen here. So we know there has to be 6 hydrogens to fully saturate 2 carbons in the compound. And here, instead of this 1 hydrogen, you have halogen groups over here, which is bromine at this time. It could be chlorine, iodine, you name it. But the halogen groups attached to this carbon here, it's just replacing one of your hydrogen here. So this one will be C2H6. This is going to be C2H5Br. Okay? So only difference here is that the bromine is replacing one of the hydrogen. That's the only difference. So in case you have a C something, maybe C4, okay, H10, okay, you have a C, and maybe I can say bromine 2, okay, and then you can consider this one, this halogen groups. It doesn't have to be always bromine, like it could be chlorine or anything, any halogen groups. Then just consider them as hydrogen. Because as you can see, the bromine is just replacing the hydrogen here, right? So you can consider them bromine is a part of the surrounding the carbon, like the other hydrogens over here. So this is the same as C4H12. Oh, sorry. Let's change this one to much more, realistic way. So if that is the case, you see that, right? I just changed this one to hydrogen here for saturation wise. Because I know there's 2 bromine still there, but we kind of consider these 2 bromine as a hydrogen here. So we have a C5H12-like compounds for this one. And then only thing you have to do is here, you have 5 carbons. That means you have to 2 times 5 plus 2 is 12. So you have to have 12 hydrogens to fully saturate the 5 carbons. which you do when you think about these two bromine as hydrogen as well. So then the degree of so this one has about 12, right? So 12 minus 12 over 2 is the 0. Okay? So whatever the gap you have from your maximum possible numbers of hydrogen minus your actual the hydrogen-like elements, which is 12. So this one is fully saturated. So there's no degree of the unsaturation. Okay? So let's do this again. So if you have C3, okay, H4, okay, Cl2, okay, you have a C3H4Cl2, okay. So in this case, same. This is halogen groups, so I'm gonna consider them as hydrogen. So I'm gonna consider them as there's 2 hydrogen here. So the unsaturation degree calculation-wise, it has a C3H6. Okay, makes sense, right? So I just switch this halogen to hydrogen for this calculation. Okay, it's not actual compound formula, but we're just doing it for the calculation. Okay, and then we have 6 hydrogen attached to the 3 carbons. We're assuming that way, okay? I know there's only 4, but because of the halogen groups. And then, if that is the case, if you have 3 carbons, you have so 2n plus 2 is what? So 2 times 3 is 6, plus 2 is 8, right? So you need to have 8 hydrogen to fully saturate these 3 carbons over here. But in here, you only have 6. So 8 minus 6 is what? 2. And divide that number by 2. Okay? That is 1. Okay? So this compound has the unsaturation degree 1. Okay? Makes sense, right? Does it make sense? Let's do. Okay, can you guys do this one real quick? Maybe I'll give you C2H2 and here. I don't know if it's realistic, but yeah. Anyway, just going. C2H2 here. About 2 minutes. It takes some time, right? Okay, so what's the number for the unsaturation degree? 1, perfect. See, it's a 2, 2, so it's just like a C2H4, but 2 carbon has to have 6 hydrogen to be fully saturated, but you only have a 4, so it's 6 minus 4 divided by 2 is 1. Okay, all right, perfect, you guys are great. So the next one is the oxygen. So if you have oxygen in your chemical formula, okay, look at this one over here, and I will change this one to hydroxyl group here. Hydroxyl group over here, okay? So this is actually easy, I'll tell you why. This is here hydrogen, this is the hydroxyl group with the oxygen here, right? So you have ethanol here. And you have oxygen attached to the carbon along with another hydrogen on it. Because it makes, so if you do this, that will be negatively charged. So you can't do it in neutral way, but it has to be in the form of a hydroxy group. That's why whenever you have, so this will be what? This one, okay? So you have 1, 2, 3, 4, 5, 6 hydrogen, 2 carbons here. And this carbon also surrounded by oxygen with the hydrogen here. So in this case, you can just ignore the oxygen there, because if this part of the carbon is surrounded by oxygen, but also can be ordered with the hydrogen attached to that oxygen here. So this is same as just this one, the saturation wise, because that part is surrounded by either oxygen or hydrogen. It doesn't really matter. So for example, if I give you C4H10O2, in this case, you just need to eliminate the oxygen here. That's it. And then C4 should have a what? 4 times 2 plus 2 is 10, right? So if you have 4 carbons there, you have to have 10 hydrogen to fully saturate. So you already have a 10 over there. So it's a degree of 0 divided by 2, 0. So degree of non-saturation is just 0 here. Okay. Do you want to do the practice one for this one too? It's pretty easy, right? Just the oxygen, just. Can I move on? We can, okay, yeah. So just oxygen, just move it and do the calculation. That's it, okay? Because the next one is nitrogen. So whenever you have a nitrogen in the sorry, in the compounds, what it looks like is actually this one. They do this because it's the group 5. You know, this can have odd numbers of the elements because it becomes really unstable radical compound. So either this can only have one lone pair. Okay. So that is the only one lone pair there. Then that makes 1, 2, 3, 4, 5. So the only thing you should know is the nitrogen in the groups, the mean groups, coming in with the 2 hydrogen on it. So if you compare to this one has only 1 hydrogen attached to this side of the carbon, and this side surrounded by nitrogen but with 2 hydrogen. So that makes C2H7N over here. So in this case, whenever you have an N in your chemical formula, do -1 on hydrogen. So you have a C4, maybe C5, and then you have a H11 and N, okay, over here. And you just need to do is you have 1 nitrogen here, right? And you have 11 hydrogen here, and try to remove 1. Because there's not only 1 hydrogen attached to it, 2. So actually what surrounds the carbon is only 1 element, which is here, but there's 2 hydrogen attached to it. So it's the same as this one. So you're gonna have this nitrogen 1. So there's 11 hydrogen there, but do -1. So it'll be 10. So you can consider this compound as C5H10 because of the nitrogen. Okay. All right. So then, if that is the case, obviously 5 times 2 plus 2 is 12, but you only have a 10. So 12 minus 10 over 2 is 1. Okay. So this one will have a degree of 1 unsaturation. Okay. So yeah, makes sense, right? Okay. Let's move on. I'll probably do the practical problem anyway before exam 2. But I think it's already done. So here's the thing. If we have that's 1. Okay. So here's the thing. Whenever you have a double bond in your compounds, okay. The major difference between the alkene and alkane is the way you have a double bond in these 2 carbons, it cannot rotate. So you know the single bond is freely can be rotated, but that's why we had all the other conformation on this the alkane. You know, you guys remember this, right? Stagger and yeah, eclipse. Anyway, so if this one cannot rotate because of this, if you have two carbons over here, they have the sigma bond in the middle, but they have a pi bond on the top of it. So when you try to rotate this bond, because of this, the P heading in the certain direction cannot be rotated. So if you have these two, has to be differently named because this is a completely different compounds. If it was just butane, looks like this. They're actually the same thing because you can just rotate it, right? So if you just rotate it, you can be in this form anyway. But because of because we cannot rotate the double bond, these two has to be treated differently. Okay, because it's not single bond, it can't be. It's double bond cannot be rotated. So in this type of thing, we have a 1, 2, 3, 4. 1, 2, 3, 4. So it'd be what? But, right? But. We have a but, and then we have a double bond ENE, and it also has all same bond, which is the same location of the double bond. It'll be 1, 2, 3, 4, 1, 2, 3, 4. So it'll be 2 butene. But still, you need to distinguish these two, right? Like I said, because it's structurally different. I mean, geometrically more specific, but anyway, different. So in this case, we're gonna call this cis form. This is the trans form. Okay. So the cis form is along with your double bond. If you're heading the other, we call this substitution groups on this double bond here. All groups here are heading the same direction. We call cis. Okay? And along with the double bond, if it's heading opposite directions here and here, top and bottom, so we could transform. Okay. So in this case, this one is our. So this one is our cis 2-butene, okay? Cis 2-butene, and this one obviously trans 2-butene. Okay? So this is how we can differently name those two when they have a different form of substitution groups on double bond here. Okay, so this is something we need to know for this alkane compounds. Because we cannot rotate the double bond, you should know sometimes you have to do transfer cis on the compounds. We have 2 minutes, so I'm not gonna do, but later we're gonna do E and D configuration as well, which is a bit more complicated form than the cis and transfer, but it's very similar. They're not the same thing, but very similar configuration we can do. Same on the other complicated compounds than this one. So I'll stop here. Okay.